Okay, so what we have here is talking about the mathematical applications of the energy required to make a phase change, in this case, vaporize, which means going from a liquid to a gas. And the name for that is the heat of vaporization. So you may see it as delta H subscript VAP in AP chemistry. And this is just the energy needed to make a phase change. If it's the vaporization of water, let's say, then you would need to add that much energy, 40.7 kilojoules per mole. And if you are condensing it, going from a gas to a liquid, you would need to remove that much energy. That's why the negative sign is there, right? And we can use these numbers in the table as like conversion factors between energy and moles of a liquid, and then we can obviously go from moles to grams. Notice that the heat of vaporization at the boiling point is a little different than what it is at room temperature. So here is just that information of this is the data that was given to us for the delta H of vaporization of water, and I can, write it so that so it looks more like a fraction. The unit looks more like a fraction, and of course, if it's kilojoules per mole, we know that that means kilojoules per 1 mole. So then I can break those up, and I'm going to highlight them here. I can either use this conversion factor or this conversion factor for whichever one that I need the right units for. So this question is asking how much energy. So I know that the last unit is going to have kilojoules on top. Needed to vaporize 25 grams of water at 25 degrees Celsius. So I start with that 25.0 grams of water, but I know that the conversion factor, or the delta H of vaporization, is kilojoules per mole. So I'm going to need to convert from grams of water to moles of water. And, actually, I don't need to do equals right now because I can just go right into the next conversion factor, which I'm going to say that 40.7 kilojoules is the energy needed to vaporize 1 mole of water. And so when I plug this into my calculator, substitute it into my calculator, I'm going to get 56.47 or 56.5, and look at how my units cancel out. Grams on the top, grams on the bottom, moles and moles, so 56.5 kilojoules, and 3 significant figures there. Because these numbers, the delta H of vaporization, do count for significant figures. So the next question is just basically going to go the other way. Calculate the amount of water in grams that can be vaporized at its boiling point with 155 kilojoules of heat. So circle the do, underline the clue. 155 kilojoules of energy goes out front. This time I'm going to use that conversion factor that says 1 mole of water will require 40.7 kilojoules of energy. And then since the question is asking about the mass, I can just put mass on the top, and that's going to, again, give us 68.611 grams, or 68.6 grams of water, right? Do my units cancel out? Of course they do. And right number of significant figures, any number coming from the periodic table has 4. And then the last one of these, calculate the amount of heat in kilojoules required to vaporize 2.58 kilograms of water at its boiling point. See if you can do this one on your own. Press pause. Remember, 2.58 kilograms, you're going to need to convert that into grams first. Okay, so let's see how we did, right? I know that 1 kilogram is equal to 1,000 grams. And that 18.016 grams of water is 1 mole of water, and that 1 mole of water will need 40.7 kilojoules of energy to vaporize. Substituting that into my calculator, 5828.4 to 3 significant figures. It's 5830 kilojoules of energy required to do that. Three significant figures, four significant figures, and kilograms, grams, moles. This one, we're going to use some information or some language that we used way back at the beginning of the year. It says a drop of water weighing 0.48 grams condenses that should be on the surface of a 55-gram block of water that is initially at 25 degrees Celsius. If the heat released during the condensation goes only towards heating the metal, what is the final temperature in degrees Celsius of the metal block? Remember, the energy lost by the water is the amount of energy gained by the aluminum. So if you think about, here's this block of aluminum metal, right? And here's gaseous water molecules, and they're going to collide with the aluminum, and they're going to give their energy to the aluminum. So the water is going to lose energy. The water is going to go from gaseous water to liquid water. And when it does that, it's going to lose energy. That energy is going to be gained by the block of aluminum. And so that's what I ultimately want to find, is what's the energy change in the block of the aluminum. So the first thing that I look at is, okay, how much energy is the water going to need to lose when it condenses? So I know I have 0.48 grams of water, and I know that 1 mole of water is 18.016 grams of water. And then from the data table, or from the table, I know that the delta H of vaporization of water is 40.7 kilojoules per mole. So what does that tell me? That tells me that 1.084 kilojoules of energy is lost by the water. But what that also tells me is that 1.084 kilojoules of energy is gained by the aluminum. And I know the formula, delta H equals mc delta T, which tells me what is the change of energy, or what the change of energy is related to the change in temperature. So if I know that the substance, the aluminum, is going to gain 1.084 kilojoules, 1.084 kilojoules, remember 1 kilojoule is 1,000 joules. So I know that this piece of aluminum is going to gain 1,084 joules of energy. It's 55 grams of aluminum. The specific heat capacity of the aluminum is 0.903 joules per gram degree Celsius. And then there's my delta T, right? I know that I needed to convert this kilojoules into joules because I know that this unit and this unit need to cancel out. When I divide both sides by 55 times 0.903, I get that the change in temperature of that piece of aluminum is 21.83 degrees Celsius. That is the amount of energy that's gained by the aluminum. So I know that I need to add that to the starting temperature of the water, which was 25 degrees Celsius. When I add those two together, I get 46.8 or 47 degrees Celsius as the final temperature of the aluminum. The aluminum will gain heat as the water loses heat energy.